already written in this way. What does it say? Well, the kinetic energy for the system as a whole, kinetic energy of just the electron relative to the nucleus. That's the one that I want. So what I do is just toss that out of the window. I don't need that. I just need this. I just need that. So, after I toss the center of mass coordinate out of the window, what I'm getting is this last equation, which is now my Schrödinger equation. It has a kinetic energy for the electron relative to the nucleus. It has a reduced mass in it, of course. And then this is the relative distance between the two particles, tallying the potential energy between the two. I don't like this rustling sound. Check this out. Okay, so here it is again, same thing. I'm going to have to write that down. This is what I have to solve. Or what you have to solve, what we have to solve together. It's a joint experience. We're party people after all. Okay, so let me expand that kinetic energy operator. Because what is it? It's the del squared. The del squared is the second order derivative in space. 3 dimensions. And we have already seen that that thing can be written in something that depends on r and something that depends on theta and phi. So that's what I'm doing here. The first two terms are the second order derivative with respect to r. That's the first one. And the second one is this lambda thing that's Legendrian. We've seen it already. That is the second order derivative with respect to theta and phi. So that is the kinetic energy. That is my potential energy part. There's something else I've done with this equation. I've divided both the left and the right by the first prefactor. You see that? On the top. The first prefactor is again this h bar over 2m. In this case 2 mu, and mu is the reduced mass. I divide all the terms by that, so that then it's away. I don't see it anymore. It's gone. That's why these first two terms don't have that prefactor, because I divided it out. It's now on the left-hand side. Okay. So this part, this guy here, that is the part on the sphere. That is the potential, the kinetic energy on the sphere. And that's what we did last time. The solutions of this part, if it's just by itself, would be the spherical harmonics. Okay? This part here depends on r. This part here depends on r. And so I have to be concerned with that part. What am I going to do? I'm going to assume a kind of a solution that has this particular form. Okay? What does it say? I'm going to say my wave function must depend on r, that's the distance of the electron relative to the nucleus, theta and phi, because these are the 3 coordinates. But I'd like to find solutions that already have this spherical harmonic part in it, so that is basically the angular dependence of my wave function, and then I want to add to it, or either not adding, but actually multiplying, because it's a product, a function that only depends on r. Okay? So relative to what we did last Wednesday, I'm going to take my same solutions, and I'm trying to find the solution for this puppy over here, this big equation, by just multiplying a function r of r. And I'm assuming if I can find that, then I'm in business. Okay, so the trial wave function here, we're going to try, has 2 parts. One part is purely angular, the other part only depends on the distance. Okay? This is a good trial. Okay, why is that? Because if I pop this guy in, here it is. I'm just going to abbreviate this. R times y, that's my trial wave function. R times y, that's the first term. Second term, same thing. Okay? But this Legendrian I've already solved, because this angular part, this y function, is a spherical harmonic, which is an eigenfunction of the Legendrian operator, this lambda squared. Okay? And so the eigenvalues were this. I don't know if you remember that, but those were the eigenvalues for the spherical harmonics. The R part doesn't do anything with Legendrian. Okay? So the Legendrian doesn't operate on that part. It only operates on the angular part. In other words, this second term completely takes care of the angular part. Done. It's not an operator anymore. This part is now just a constant, because these are just numbers on this side, times the function, the wave function. Okay? So that's good. The third term is a potential energy term. I don't know what to do with it yet, so I'm just going to have my wave function just sit there, r times y. And then, all the way on the right-hand side, same thing. Okay, so here, r times y, r times y, r times y, and r times y. The first term has the operator r squared in it with a couple of little r's on the left and right. But clearly it only depends on r and not on y. So let's walk through this equation one more time. R times y, the y doesn't do anything with this operator. The y doesn't do anything with this operator because this is just a constant. Here too, the y doesn't do anything here, and not here either. So I can just simply divide out by y. Okay? Consequently, I have now an equation that only depends on the radial part of the wave function, which is what I would like to solve. That's the part I would like to solve. So I've done that. I've divided out the y, so I have only the r's, the big R's, capital R's, and I've also grouped those middle part, those middle terms, put them between parentheses. Okay? Because this is kind of an operator that is taking the derivative of. This is just a multiplier. Put all the multipliers together and then multiply it by big R. Now, how can I interpret this result? I interpret this as follows. This term is the kinetic energy operator along my radial coordinate, because it has a second order derivative with respect to r in it. Okay? So this is the kinetic energy operator for the radial part. What is this ugly beast? This is the potential energy. Okay? We already had this Coulombic interaction, but there's something else. Something that depends on L, and L is the angular momentum quantum number. Why would that be there? Well, if something has angular momentum, actually it adds to the potential energy, because if you have something that swing around something like this, clearly there's a potential, there's a force there, right? It wants to kind of shoot off. That force is associated with a potential. That's the centrifugal force. The centrifugal force, which is always associated with angular momentum. So if my wave function, aka my electron, has angular momentum, there must be some sort of a centrifugal force at play, and its potential looks like this. Together, that is my potential. Okay? Coulombic interaction, centrifugal forces, together is what my particle experiences. That's what pulls and pushes on my particle, my electron. That's what my particle sees. Two things. It has kinetic energy, it has potential energy, forces that act on it. And now we have figured out what they are. This is, of course, what I'm going to try to solve. I'm going to try to solve this R so I can find E. Okay, so I'm going to, because I just made a big deal out of this term, I'm going to rename it. I'm going to call it the effective potential, with the 3 factor in front, which turned out to be useful to define it that way. So this whole thing here is that. Okay, going to really try to solve this thing. The remaining task is to really solve this problem. And the way to do it, let me just quickly go back here, is to do the following. This equation here needs to be solved. I see here, in this term, there is little r times r. It's pretty ugly, okay? I don't like that. There's also 1 over r here. What if I now multiply this whole equation by r, little r? Then this 1 over r disappears. That's good. Then here, there's going to be in little r. And here, also little r. Why is that good? Because now I have here little r, little r, and here, little r. Okay, so I'm going to rename that function pi. Why not? That's what the next slide says. Okay? I'm going to rename that function little r, big R, pi. I'm not interested in pi. I'm interested in r, but if I solve for pi, I have r2. Okay? That's the thinking here. So, you can do that. I can now write the Schrödinger equation for the hydrogen atom in the following way. You may not like this, but this is just the way it is. And this is, I mean, think about it. This is the entire problem. This is the entire problem. We have not made any approximation yet. Okay? We have not made a real approximation. Everything is so-called analytical. So this must be correct. If I'm able to solve this equation here, I'm going to be very happy. I'm going to be beaming. So, second order derivative of pi, then potential term times pi, then constant times pi. That's it. If I solve for pi, I have big R also, because big R is simply pi divided by r, and I'm done. Can it be done? Of course it can be done. It's not easy, but we rely again on very smart people that came before us. Okay? And they have figured it out. Okay? After many wet Sunday afternoons, this equation rolls out. Oh my God. What's going on here? It's the solution, folks. This is the radial wave function. This is the radial wave function of the electron in the hydrogen atom. This is it. Absolutely no approximations made. This is 100% true and accurate. It looks a little bit ugly, but again, let's try to go through it and maybe you relax a little bit. Okay? So let me see what happens. R and L. NL are the quantum numbers. We've seen them before. N and L. N, principal quantum number. Little l, angular momentum quantum number. Therefore, this is truly a wave function. It's a quantized thing. It has labels. Only certain solutions are allowed, other solutions are not, and solutions that are allowed have integer quantum numbers, N and L. It depends on R, because it's just a function of the radius. The angular part I already know. That's the spherical part. That's the spherical harmonics. I'm talking just about this radial part. Here I see the first term, constant. Z is 1, okay? N is principal quantum number. A is going to be also a constant that I'm going to define in about 73 seconds. Then I have here a whole bunch of garbage that is just plugging in your numbers, okay? N is principal quantum number, L is angular, just whatever the indexes are, and you can do the math. It's just, it looks terrible. It's just a number, okay? If I say 2, you're not scared, but if I say that, you're scared. But in fact, that could just be 2, okay? So don't be scared. Then the last part, this is really the functional part. This is the part that really depends on distance. The rest is just constants. Let's look at this. It has 3 ingredients. 3. A rho I don't know what that is yet. I'm going to determine that in 2 seconds. It's going to be directly proportional to r. It's r times some constant. Times to the power L, rho to the power L, which is rho to the power of the angular momentum quantum number. Then a big L with some indices. That is a polynomial function. And then a exponential function, which is a decaying exponential. Since rho depends on r, that basically means that at long distances, all the solutions go to 0. Okay? So all the wave functions have something here close to the nucleus and at the far end peter out. Okay? There's a couple of things I have to define. First of all, this rho thing, what is it? I told you, it's directly proportional to r with a prefactor. Prefactor depends on z, which is 1, n, which is a principal quantum number, and a, I still don't know what a is, so let's get to it. A is also a bunch of constants. Remember, the Hamiltonian had a whole bunch of these natural constants in it. A is a collection of those. Also includes the reduced mass, mu, as you can see. So, it looks terrifying, but in the end, it is a function that is having multiple ingredients, quantum numbers, n and l, distance r, okay? But then I'm good to go. I can just program into a little script and generate these functions, okay? So let's have a quick look at the first 3 of them, okay? They don't look really that terrible, to be honest. When n is 1, l is 0, then this radial function is a constant times 2, don't be scared of 2, just a number, and then the complex exponent, aka a constant decaying exponential. So that basically means, this is my nucleus, the wave function simply goes like that. That's the simplest, lowest energy radial wave function. Second one, n equals 2 possibilities. L can be 0 or 1. You can see that corresponds to the 2 as in a 2p over time. Same thing, but now in front of this decaying exponential, there's simply now a kind of polynomial, 2 minus rho. Okay? 2 minus rho means that this thing has a node, because it can be 0. Whenever rho equals 2, that function is 0. So this is something that actually has a wiggle in it. It's no longer a decaying exponential, but a decaying exponential with one wiggle. This one simply has rho in it. If I'm ramping up the quantum numbers n and l, then these functions get progressively more complicated, mainly in terms of whatever this polynomial is. It can have longer, more terms in it, so more and more wiggles. But that's it. So the middle term here is the wiggly term. This term always decays. And that's basically what these functions look like. Here are several of them. You may have seen this before, but I don't think you knew exactly how to calculate them. Now you know. So, the first one, simplest solution of the radial wave function, all the way in the left top, is this decaying exponential. N equals 1, L equals 0. Right underneath, N equals 2, L is 0. But do you see? It has one node, one place where it actually is 0. It dips below 0, and then comes up again. It never crosses the 0 again. Okay? It never crosses this y-axis again. And so it kind of decays, now from the bottom decays to 0. You see that? Then if I go to, this is the middle part now, on the top middle, R 3,0, N equals 3, L equals 0. Same mechanism, but now there's 2 nodes, 2 places where the wave function can be 0. So it has an extra wiggle in it. Now you can see that actually this is truly a wave. You see? It has like dips and tops, troughs and valleys. But there's places where it crosses the zero line, which means it has nodes, places where the electron cannot be. Wherever the wave function is zero, the probability is absolutely zilch, and therefore the electron cannot be found in those regions. The next three are for L with higher values. This is R 2, 0, N equals 2, L equals 1. That's a 2p radial wave function. It starts at 0, goes up, comes down. On the top, same thing, but now an extra node, because N equals 3. And then if I ramp up L, actually it doesn't go through 0 anymore. It goes up, comes down. But the top is now in a different place. This one and this one have different maxima, which has to do with the size of the orbital, how big the orbitals are. These functions are just plotted with the mathematical function on the last slide. That was a direct solution of the Schrödinger equation. That's where these shapes come from. These shapes are not made up, I just want to stress that. Not made up. These are actual solutions of the problem. We just define the problem, solve it, and this is what's rolling out. So, what do we have? We actually have now the full solution for the hydrogen wave function. This is it. The hydrogen wave function is the R times the Y. The radial part times the angular part. The radial part we just solved. The angular part we did last Wednesday. When you were thinking about the midterm, I was getting excited about these angular parts. Okay? But now you are excited too, I can see it. So what again is this relation between these quantum numbers? We know what it is. Same as before, but let's walk through it one more time. N, 1, 2, 3, 4. Principal quantum number. L, slaved to whatever n is. It runs from 0 to n minus 1 in integer steps. Why is this so? Because it looks cool? No. This is what the math tells us. It has to be this way. Okay? The ML follows from the spherical harmonic part of the wave function, and it is slave to whatever L is. The only valid solutions mathematically to this are the solutions where ML runs from negative L to plus L in integer steps. Those are the mathematical results. It just rolls out. So, what then are the energies for these wave functions? Because remember, there's always two parts to the Schrödinger equation. One, the wave function. Two, the wave function has an energy associated with it. What is the energy of the electron when it sits in this wave function? The energies is this. Really interesting. The first part between parentheses, I'm going to say, is a bunch of constants again. I hope you agree with that. Z is in there, nuclear charge, which is 1 for the hydrogen atom. Mu, the reduced mass. And then all the other guys are in there too. And then outside of the parentheses, 1 over n squared. That's the principal quantum number. What does that mean? It means that the energy of a given state, of a given wave function, of a given state in which the electron can sit when it's part of the hydrogen atom, it can have energies that are only this, and it only depends on n. It does not depend on L or ML. See that? It's kind of remarkable. In the hydrogen atom, the energies only depend on the principal quantum number. The energies do not depend on the angular quantum number and the magnetic quantum number, ML. This has everything to do with the fact that in the hydrogen atom, the electron and the nucleus are on their own, and the electron is not interacting with anything else. Then we solve this problem. This is what rolls out. As soon as we add anything to it, this breaks down. This energy is no longer just dependent on n. But for now, it is, because it's just one electron. Electron only interacts with the nucleus but nothing else, and it's a very clean solution where the energies only depend on the principal quantum number. So here's basically the states in which the electron can sit. The electron can be described by any of these lines, because any of these lines correspond to valid solutions of the Schrödinger equation. Because I have these quantum numbers, I can just fill in the numbers and generate these functions. The electron could be in this one. The ground state of the hydrogen atom is when the electron occupies n equals 1. In that case, L is 1, ML is also 1. Could be sitting in there. And typically, if you have a hydrogen atom that's floating around in space, that's the state the electron sits in. Unless you don't do something to it, if you give it a whole bunch of energy, by light or something else, it could occupy any of the so-called excited states. For instance, n equals 2, n equals 3. In n equals 2, there's two values for L. L is 0 and L is 1. L equals 0 generates only 1 ml value. L equals 1 generates 3 ml values, so there's a total of 4 states. They all have the same energy. They are degenerate. They are degenerate. So if the electron has principal quantum number 1, it can sit in, and if it has 2, it can sit in any of these states. It can only sit in one of these states because all of these are individual solutions of the Schrödinger equation. This state is not the same as that state. This is a different state than this. They just happen to have the same energy. That's the only similarity between the two. On the top, I have many more because now n equals 3 and L can have a total of 3 values, 0, 1, and 2, and each one of those generates their own ml values. I have a total of 9. 9 states. All of them, I can't emphasize this enough, all of them are individual solutions of the Schrödinger equation. The electron can occupy any of them, okay? Not at the same time, one at a time. They're all different, they all are orthogonal to one another. That's another thing because it's a complete set. Complete set of eigenfunctions of the Hamiltonian. All of these wave functions you see here with specific energies, they're all mutually orthogonal. Now there's a very nice relation between the principal quantum number and the number of degenerate states. As you can see, I only have one value for n equals 1. I have 4 for n equals 2, and a total of 9 states with the same energy when n equals 3. And in fact, I can write down a so-called degeneracy parameter called G, which can be computed in this fashion, 2L plus 1. 2L plus 1 is a number of ml states. And I'm counting how many different L's I have. Okay, so I'm adding up basically the number of L's, and then for each L I have 2L plus 1, which is the number of ml states. And if you add them all up, you get n squared. Kind of cool? That's true, because 2 squared is 4 and 3 squared is 9. So that adds up, and therefore that is a very useful formula to keep in mind. The number of individual eigenstates having the same principal quantum number is n squared. Okay, so pretty cool. I think this is kind of a good milestone in this course because we have now the official eigenfunction or the quantum mechanical description of an electron in the hydrogen atom. It's analytical, no approximations made. We know what the energies are like. So I think on Wednesday we're going to examine or study what these solutions tell us. Okay? What do they tell us? What do the orbitals look like? And what kind of properties do they have? All right, folks. See you on Wednesday.